We're on to everybody's favorite topics, trig and complex numbers. So we're going to start by just graphing these complex numbers. Remember the complex plane is like the xy axis, except for the x is the real axis and the y is the imaginary axis. So -1 is the real component and 3 is the complex component. So we're going to go -1 and then up 3. 1, 2, 3. Okay. This is point A. And B, we're going to go ahead and do 3. So positive 1, 2, 3, up 1, 2. That would be B. And point C would be -2, -1. All right, so here's the deal, is that we can plot these vectors, or we can plot these complex numbers as vectors. So if I start from the center, I'm moving, for B, I'm moving to the right 3 and then up 2. Okay, so the x component is 3, the y component is 2. I could do it for all the rest of these too. We can plot these as vectors if we want. And then the length of the vector is the magnitude, or the radius, or the radius in trig, or we can call it the modulus. Yeah, modulus. That's another word for that. Okay, so the magnitude. All right, so a couple important things to remember is if we just think about trig, if I have my vector here in the imaginary plane, I'm moving over in the x direction some length. So over in the x direction, we're going to call that A for the real component. To the real component. Okay, remember that's just r cosine theta, or the magnitude of the vector times cosine theta. We're going to call the change in y B, which is the complex, it's the imaginary component. Okay, so these are really important to remember, that r squared is equal to a squared plus b squared. I went ahead and just solved for r over here. Our a is really our x, it's equal to r cosine theta, and b is r is equal to sine theta. I think another thing to remember is that our angle, the angle here, theta, can be described by tangent. So the tangent of theta is equal to the y, which we're going to call b, over a. All right, so the standard form of a complex number is like the ones we saw in our warm-up. So the vector z is equal to a plus bi, and the trig form of a complex number is basically the same thing. We're just going to replace out the a and the b. So let's do that really quick. If I have z is equal to a plus bi, well, I have this equation right here that replaces a. So z is equal to r cosine theta plus, I'm going to put the I in the front, times b, which is r sine theta. I'm going to GCF the r out. So r is equal to cosine theta plus I sine theta. So this is the trig form of our complex number. So just using r and theta to describe the lengths. Okay, so write the complex number as its absolute value. This is aka magnitude. So what is the magnitude of the absolute value of the complex number? Okay, so if I go back to my example, we're going to be looking at examples of the point C here. So -2, -1 is our component. So I know that, let's just regraph this. 1, 2, negative 1. So the vector will look something like this. So in order to get my magnitude, I can do r squared is equal to a squared plus b squared. My a is the real part, which is negative 2, and b is equal to negative 1. So r squared is equal to negative 2 squared plus negative 1 squared. So r squared is equal to 4 plus 1, which is 5. So r is equal to the square root of 5. Next, let's do one more. This 3 is my a component, 2 is my b component. Again, if we regraph this, 1, 2, 3, up 1, 2. Okay, what is r? R squared is equal to a squared plus b squared. So that would be 3 squared plus 2 squared, which is equal to r squared. So r squared is equal to 9 plus 4, which is 13. So the square root of 13 is equal to r. That is the length of the absolute value or the magnitude. Okay. All right. The next thing, we're only going to do 3 things with these trig forms of complex numbers. So we do need to convert the complex number into trig form. So remember, trig form is r times cosine theta plus I sine theta. So I'm going to go ahead and draw this out real quick. Let's see. In the x direction, we're going to go square root 3. In the y direction, we're going to go 1. Okay. So I need to figure out what my angle here is, because I need the angle for my trig form. And the other thing I need is my radius, or my modulus. How long is it from the center to the end, the initial point to the terminal point of the vector. Okay, so to get r, I remember r squared is equal to a squared plus b squared. So r squared is equal to the square root of 3, that equals a, equals b, squared plus 1 squared. So r squared is equal to 3 plus 1. So r, I'm going to go ahead and square root that. That's 4. So r is equal to 2. Okay. So r is equal to 2. So I'm going to use the tangent of theta is equal to 1 over root 3. And I recognize that as root 3 over 3. So what angle would give me a tangent of root 3 over 3? I can see that this is a 30, 60, 90 triangle. So theta is going to equal, let's see, that's the smallest side, so 30 degrees, or pi over 6. Okay, so in trig form, a is equal to 2 times the cosine of pi over 6, and here b is equal to 2 times the sine of pi over 6. You can plug those in and see if it works. So z is equal to, my radius was 2 times the cosine of pi over 6 plus I times the sine of pi over 6. And that is that. Okay, next example, 2i. So let's just do a little graph. So 2i just goes up 2 units. So it's going to be something like that. Let's see. Something like that. So what is this angle theta? Well, that angle theta to me looks like pi over 2. It's going straight up. And what is our r, or what's the length here? Well, that's 2. So z is equal to, the r is equal to 2 times the cosine of pi over 2 plus I times the sine of pi over 2. I shouldn't write them like that. Pi over 2. And that's it. Okay, the last thing. Represent the complex number graphically and find the standard form. Okay, so we're going to do part A. Z is equal to the square root of 8 times the cosine of negative pi over 3 plus I sine of negative pi over 3. Okay? So thinking about our trig form, remember this trig form is written like r times the cosine of theta plus I times the sine of theta. So it looks like my root 8 is my r, and my angle is negative pi over 3, okay, for both of these. So I go ahead and look. So negative pi over 3 would be negative 60. So negative pi over 3 is equal to theta. And then my r is equal to the square root of 8. So if I want to figure out what my standard form, which is z is equal to a plus bi, I really just need to evaluate this. So z is equal to the square root of 8 times, okay, let's see, negative, this is going to be negative, or the square root of 8 times cosine pi over 3 of negative pi over 3, which is 1/2, okay? So square root 8 is on the outside. Cosine negative pi over 3 is 1/2 plus I. The sine of pi over 3 is root 3 over 2 times 8, square root 8, sorry. So times the square root 3 over 2. So I get z is equal to root 8 over 2 plus I square root 24 over 2. Distribute. Okay, so 8 is 4 times 2. So we get 2 root 2 over 2 plus I. This is 4 times 6. So times 2I root 6 over 2. My 2's cancel, giving us root 2. Oh, and this is negative. 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 Minus the square root of 6, I. So I usually put the I in the front because then it doesn't get lost back there. Last one. So we already did A. We're going to go ahead and look at B here. Okay. So 3 over 2 cosine 11 pi over 6 plus I sine 11 pi over 6. So I'm going to go ahead and just draw out a triangle at 11 pi over 6, which is 330. So this is 11 pi over 6, which means that my reference angle is pi over 6. So across from pi over 6 would be negative 1/2, root 3 over 2, and 1. Okay, so I'm going to go ahead and evaluate. Z is equal to 3 over 2 times cosine would be root 3 over 2 positive plus I times negative 1/2 negative. So we get 3 root 3 over 4. So when I distribute, plus 3 times negative 1 is negative 3 over 4 I. And that's how it's done.